going to do some more work with heat calculations, and we're going to look at phase changes, which means we want to figure out the total amount of heat energy required to go from, say, really frozen ice to melting, and then heating to boiling, and then to steam. So there's different steps that we need to do, and we need a few numbers. So if you have this paper, we can add the numbers that we need, or you can just jot them down in your notes somewhere handy. So basically, when you're looking at boiling or condensing, so it's going to steam, or when you breathe out, it looks like fog, that would be condensation. So what we would need is heat of vaporization, and the way that we write it is, need a marker here. Maybe I'll make a blue. Is H with a little sub V like that. And for water, heat of vaporization is 2260, and that's, let's see, what's our units? Joules per gram. Okay. We also need our heat of fusion. So anytime you are freezing water or melting water, we write it as H with a little sub F, little tiny F like that. And for water, the heat of fusion is 334 joules per gram. Okay. And then we need to also have, since we're doing some work with ice, we need the specific heat capacity for ice, which is a little different from water. So ice, and if you remember, specific heat, we abbreviate it with a capital C, little p, is 2.06. And remember, the units are joules over grams times degrees Celsius. So that means that it takes 2.06 joules to raise 1 gram of ice 1 degree Celsius. And then steam is really similar. This is very interesting. So the specific heat is 2.02. Isn't that interesting? Very similar. And of course, joules, grams times degrees Celsius. And then, just for good measure, let's write water again. You probably have this memorized by now. Well, let's just write it down. 4.18 joules per grams degrees Celsius. Okay, so those are the numbers that we need, and we're just going to use them in a phase diagram. So that's what we're going to do next. Okay, we got that? All right. All right. So a phase diagram keeps track of phase changes. So you have a paper, a handout. Where am I in it? Oh, here we go. That says heating curves and thermochemistry on it. And you've got a drawing that looks like a graph. Oops. And it keeps track of what's happening. So you just have to kind of think about this. Let's say that you have ice, and so you just have to kind of establish a spot on your graph where water's going to melt, so at 0 degrees Celsius, and where water would boil at 100. So you may have noticed in our lab that water actually boiled around 97 degrees, and maybe your ice froze a little bit colder than 0. This is kind of in general at standard temperature and pressure, which means sea level, and so we're just going to use 0 and 100 to make it a little more simple. So what would happen if you take ice, you kept it in the freezer, and you warm it up? It's going to warm up until it reaches melting, and it's going to stay at that temperature until all the kinetic energy throughout is the same. All those molecules are moving around the same, and then after they're all melted, you're applying heat. It's going to go up, and then at boiling, it's going to boil at 100 degrees until all the molecules are doing the same thing. You've got all the same heat energy throughout, and then if you continue to heat it, you can have steam that gets hotter. Okay? So we've got all these different places, and at each step, something different is going on. So this first step, where you're heating ice, you're going to use your mass times your temperature change times the specific heat of ice. Okay? I'm going to put ice, so you remember, this is when it's a solid, right? And what we're solving for should look familiar. It's heat, right? Okay. So when you have a change in temperature, right away you should go, oh yeah, I used the one where there's a change in temperature. So where else do we have that? Oh, we have it right here as well. Let's take care of that. So while it's a liquid, you have mass. You've got your change in temperature, which will always be 0 to 100, right? And then the specific heat of water. So and then where else is it changing? Right up here. So if you've boiled it all the way, it's all steam, you're continuing to heat it again as a gas, you will have mass, change in temperature, and then this time specific heat. It's not letting me, I think, because it's little pictures here. Specific heat of steam. Just pretend like there's one there. Oh, what's going on there? Now, what we haven't taken care of is when there is no change. You're still inputting energy into that, but all the molecules have to get to the same kinetic energy before you have an increase. So we do have to take care of this. So we have our mass, and then if you remember here, this was the heat of fusion, melting or freezing. So, okay. And then the same thing, we don't have a change in temperature, right? We don't need that. And then up here we have mass times the heat of vaporization. Now, in our case, we're doing water, but you could do this for any substance if you know the heat of fusion and the specific heats for all of those intermediate steps. Now, you guys can do all of these things. This is just multiplying, and then you add them all up. If you want the total heat that you'd have to put in, you would figure out each one separately, and then you would add them all up.